So we are going to continue what was supposed to be the first talk, and it's lifting ideas from propositional logic to first order logic. And Maria Paola Bonacina from Verona will tell us about it. Please go forward.
Thank you very much. So I'm going to talk about conflict-driven first-order decision procedures. And this is based on the joint work with Sarah Winkler and joint work with David Plested. Now, the talk is organized in 4 parts. I'm going to give some ideas about what is going on in automated reasoning beyond SAT and SMT. Then I'm going to present Sdgs, which stands for Semantically Guided Goal-Sensitive Reasoning, and is a method which realizes conflict-driven reasoning in first-order logic. And then I'm going to show you recent investigations on whether and how Sdgs yields decision procedures for EPR and other decidable fragments in first-order logic. Please feel free to make questions at any time. Now, in automated reasoning, we have different tools based on logic, and usually they are enumerated, so to speak, from the decidable towards the undecidable, or from the least expressive logic towards the most expressive, mentioning SAT solver, SMT solver, theorem provers for first-order logic, and proof assistance for higher-order logic. But the message I would like to give in this introductory part of the talk is that the current research trends are challenging these traditional borders. Because much of the research in automated reasoning today is about integration and hybridization of techniques, integration of different methods, integration of reasoning methods within application tools, and migration of features that are considered typical of one kind of methods to others. For example, at the border between higher order and first order logic, we have solvers and provers embedded inside or invoked as back-end to proof assistance. And even more advanced and interesting, now we have higher order automated theorem provers. Superposition, which is resolution with equality built in, has been generalized to higher order logic. And so now we have superposition-based automated theorem provers for higher order logic. This is an exciting new development at the border between higher order and first order logic, where we witness the migration of techniques from first order to higher order. But also at the border between first order logic and SMT and SAT, there are a lot of new things happening. There are approaches for having quantifiers, which is really the essence of first order reasoning in satisfiability modulo theories. And we have, which is, if you wish, a migration of something from first order logic to SMT. But we also have a migration in the other direction with the lifting of conflict-driven reasoning as in CBCL to first order logic, which is the topic of this talk. Now, what is the conflict-driven reasoning? In this audience and in this workshop, we know this pretty well, but let's remind us of the general paradigm. The idea is that we have a procedure to determine the satisfiability of a formula. This procedure searches for a model by building candidate models. A model is typically represented by a series of assignments, and assignments are propagated through formulas in order to get what are the logical consequences of these assignments. And this propagation usually is something fast. When a conflict arises between the candidate model and the formula, it is explained by inferences in such a way that the dilemma can be learned in order to avoid repeating the same search and the same conflict. The conflict is solved by fixing the model to satisfy the learned lemma. And the key thing is that while propagation are relatively inexpensive inferences, the non-trivial inferences that are more expensive are confined to explain the conflicts, to respond to the conflicts and fix the model accordingly. Now, this paradigm was brought forth by CDCL for SAT, and then it was extended first to several fragments of arithmetic with the conflict-driven satisfiability procedures for sets of literals in various fragments of arithmetic. Then the model constructing satisfiability paradigm by Dejan Jovanovic and Leonardo De Mura generalized it to SMT, showing how to combine in a conflict-driven manner propositional logic and one theory. And the CDSAT framework, conflict-driven satisfiability, shows how to do it for not only one theory, but for a generic combination of theories, and also for satisfiability modulo assignments, which means first-order assignments may also be part of the input. Now, what about first-order logic? Here is where SDGs comes into the picture. And then the next question is, can we get decision procedures from SDGs? And the answer will be mixed. So SDGs will decide EPR and other fragments, but it will not decide some other fragments. But what is interesting is that the decision procedures that we get from SDGs are conflict-driven and model constructing, which is rare for decision procedures in first-order logic, because, for example, if you consider resolution-based decision procedures, when they terminate and discover that the set of clauses is satisfiable, they typically yield a saturated set of clauses, which, however, does not represent a model, because resolution is not a search procedure that proceeds by searching for models and solving conflicts. Now, let's see the basics about SDGs. We have an input set of clauses. The method is semantically guided, which means it adopts a fixed Hilbert interpretation I to guide the search. In general, this interpretation is not restricted. Any Hilbert interpretation will do. But for this talk, we are going to consider only sign-based semantic guidance, that is either the all-negative interpretation, which satisfies all the negative literals, or the all-positive interpretation, which satisfies all the positive literals. Now, if the interpretation used for guidance does not satisfy the set, we need to search for a model. SDGs works with a trail, which is a sequence of clauses with selected literals. This trail represents an interpretation, which in essence is a modification of the initial interpretation I by satisfying the selected literals. And then the method either gets a trail such that the induced interpretation is a model of the set of clauses, or else it discovers a contradiction which tells that the set of clauses is unsatisfiable. Now, let's see the method through examples rather than going through the theories. Suppose we have a set of clauses with PA, not PX, or QFY, not PX, or not QZ, very simple, so that it fits on one slide. And assume that the guiding interpretation is all negative. Clearly, the guiding interpretation does not satisfy the set because PA is positive. So what SDGs does, it performs an SDGs extension step, which puts PA on the trail, and PA is selected. You see it is in bracket and it is red, because it's the only literal in the clause, and therefore we have no choice but to choose this literal. However, SDGs has a preference for selecting the positive literals when the guiding interpretation is all negative, and the negative literals when the guiding interpretation is all positive. Now, with gamma 1, we have an interpretation which satisfies all the negative literals except PA. Clearly, such an interpretation is not a model for not PX or QFY, because it is sufficient to instantiate X with A to get instances that are not satisfied in this interpretation. So we add this instance, not PA or QFY, to the trail with another SDGs extension step, which is generated by unifying not PX with the selected PA so that X gets A. The positive literal is selected, and the negative literal not PA is mapped backward to the positive PA selected to remember, so to speak, that this literal that was true in the initial interpretation is now false because we are modifying the interpretation in an attempt to satisfy the set. Now, with gamma 2, the induced interpretation does not satisfy the third clause, the all negative one, because it does not satisfy all the instances where X is instantiated with A and Z with Fy, since now we have these two red literals PA and QFY being true. So another SDGs extension with the appropriate MGU put this instance on the trail. And again, now we need to choose a negative literal because they are both negative, and SDGs chooses the one that is assigned rightmost, that is not QFY because it is assigned to QFY, in the sense that the selection of QFY makes not QFY false. Now this clause is a conflict clause because all its instances are false in the current interpretation I gamma 3. So we need to solve the conflict. The way SDGs solves the conflict in this case, when the conflict clause is such that all its literals would have been true in the original interpretation, in this case because they are both negative, is to move the conflict clause to the left and precisely move it left of the clause whose selected literal QFY makes not QFY false. So you see this move. Now, the interpretation induced by gamma 4 clearly satisfies not QFY, because it's like this literal was flipped. However, now it is not PA QFY which is in conflict, because both its literals are falsified. But this clause is not all negative, it has a positive literal, and therefore SDGs resolution intervenes to resolve the third clause with the second on the selected literals, and the resolvent, which is not PA, actually replaces the second premise, because resolution in SDGs is a very restricted form of resolution which applies only between clauses on the trail, applies matching and not unification, and uses the resolvent to replace the second parent, the one which is not I all true, in this case, the one which is not negative. Now, not PA is in conflict because PA is true. So it moves to the left of the clause which makes it false, it resolves, and we get the contradiction by SDGs resolution. So how does this realize conflict-driven reasoning in first-order logic? Picture a clause L1 through Lk, a disjunction of literals, where we select literal Lj. The analog of a decision in CDCL is an SDGs extension which puts an instance of a clause on the trail and selects a literal. Selecting a literal means adding to the interpretation, to the candidate model, all the ground instances of the selected literal that are needed to satisfy this clause. Not that not all of them may be needed, because some ground instances of this clause C may be already satisfied by previous selection already made on the trail. But when we add an instance of a clause and we select a literal, we add all the remaining instances. How does propagation work? Clearly, we are going to have a conflict clause when the current interpretation I gamma induced by the current trail gamma makes true all the complements of the clause. So we have a clause L1 through Lk, and all the complementary literals are true. So this one is in conflict. And we have an implied literal when all the literals but one, Lj, are false in the current interpretation. So to be precise, it is not enough that they are false. What we need is that their complements are true. And then this literal Lj is implied because making true all the ground distances of Lj is the only way to satisfy this clause, and therefore it gets selected and it is an implied literal. And then, as we saw in the example, conflict solving involves conflict explanation by Sdgs resolution and learning by Sdgs move. So we don't have a proper backjumping, but a rearrangement of the trail with the clause migrating to the left, because the way we read the interpretation from the trail is from left to right, and therefore our clauses at smaller positions have priority. Now let's see an example where Sdgs finds a model. Suppose we have these 4 clauses, and suppose again that the guiding interpretation is all negative. Clearly, the first unit clause Pxxa is not satisfied. So we put it on the trail and we select Pxxa to make true all the ground distances of literal P, where the first 2 arguments are equal and the third argument is A. At this point, not all instances of the second clause, the one that starts with Px, Y, W, are satisfied, because we lost precisely all those instances of the 4 that were made true by the third negative literal, because I is all negative, but now they are no longer true because we made Pxxa true. So we do an Sdgs extension unifying this negative literal, not Pxzw, with Pxxa. Remember that every clause has its own variables, so the 2 x's are different. And we get an instance that we put on the trail. We can select either one of the 2 positive literals. Suppose we select the second one. Now this means that we have a model where all the negative literals are true, except those of the form Pxxa and those of the form Pyxa. But now these 2 literals have an intersection, because clearly all instances of Pxxa are also instances of Pyxa. So what Sdgs does when there is an intersection, it applies a rule called splitting to split the second clause and distinguish and do a partition where the first clause has as a selected literal a literal whose ground instances are those in the non-empty intersection with the first, whereas the second clause has a selected literal that captures the other instances. So here x, the first 2 arguments are equal, and here the first and the second argument are different because we have the constraint y different from x. So splitting is the rule which introduces constraints in the system. But now, this second clause is satisfied because in the interpretation induced by this trail, Pxxa is true, and therefore all ground distances of this clause are true, and therefore we can remove it. And we are left with these 2 clauses, which basically means that the final interpretation satisfies all negative literals except the literal where the third argument of P is A, because this clause captures those where the first and the second argument are equal, and this clause captures those where the first and the second argument are different. Now, this interpretation is a model for S, because it obviously satisfies the first clause, and for all the other clauses, if the third argument, if we consider an instance, a ground instance, where there is a literal, where the third argument of P is A, it is true with a positive one, either this one or this one or this one. Otherwise, with a negative one. Now, is termination on this set expected? Because Sdgs terminated, found the model, but we could ask, was it expected that it terminates? Is this something perhaps special or trivial? Yes and no. Why? Well, hyper-resolution, which is a semantic resolution with sign-based semantic guidance, does not hold on this set. So it is not so obvious that a method with sign-based semantic guidance would hold on this set. Now, what is a semantic resolution? Semantic resolution is resolution restricted to generate only resolvents that are false in a given guiding interpretation I. What is hyper-resolution? It is a semantic resolution with sign-based semantic guidance. So, for example, in positive hyper-resolution, we generate only positive clauses because we assume as a semantic guidance the all negative interpretation. And therefore, in order to generate only resolvents that are false, we generate only positive resolvents. We take a non-positive clause C called the nucleus, and we resolve it simultaneously with as many positive clauses as needed, termed satellites or electrons, to resolve away with the simultaneous MGU all the negative literals in the nucleus and get a positive resolvent, which is false in the guided interpretation. Now, let's see what hyperresolution does on this set. Hyperresolution generates infinitely many clauses. So the termination of SDGs is not an easy thing for a semantic-based technique. Positive hyperresolution generates infinitely many clauses from the first two clauses because it takes the second one, the mixed one, as nucleus, the first one, PXXA, as satellite. They resolve and generate a positive clause, which then can be used as satellite again, and so on forever. And negative hyperresolution generates infinitely many clauses from the third and the fourth clause. Now, this is actually a well-known example which defeats hyperresolution. But on the other hand, termination on this set is not so surprising because this set is in the Bernays-Schonfinkel class, which is also known as effectively propositional logic. It comprises all the sentence of the form exist star for all star phi, where phi has neither quantifiers nor functions. When we translate it into clausal form, we apply scholemization so that all the existentially quantified variables are replaced by constants. There are no function symbols, the Herbrand base is finite, and so we get decidability. And indeed, there are multiple decision procedures for this fragment, including DP-LLSX by Ruzicka and others, non-redundant close learning by Alaghi and Weidenbach, small model close learning by Fiori and Weidenbach. Now, does SDGs decide EPR? Yes, we shall show this shortly. Does SDGs decide other fragments? Some, but not all. Does SDGs allow us to discover new decidable fragments? Yes. So let's see how. Well, first, let's remember how SDGs makes progress. In SDGs, we call this joint prefix of the trail the longest prefix with no intersection of selected literals. Now, suppose that the problem is not solved, which means we didn't get to the empty clause, so we didn't find unsatisfiability, and we didn't find the model yet. So there are two situations. Either the trail is different from its disjoint prefix, or else it is equal. If it is different, it means that either there is some intersection between selected literals that we remove by SDGs splitting, or else there is a conflict to be solved. If they are equal, but the set of clauses is not satisfied, it means that for some clause in the set, some ground instance is not satisfied, and then extension applies to extend the trail and therefore the current interpretation. Why am I saying all this? Because from this knowledge of how SDGs makes progress, behind this there is a lifting theorem that tells that SDGs extension applies under these circumstances, and another theorem that tells that the other rules apply otherwise. We glean that not termination may come only from infinitely many extensions, because removing intersections and solving conflicts are finite activities that require only finitely many steps. Then, in order to get a decision procedure, we also need fairness of a derivation, which means progress is made whenever possible, If an extension adds a conflict clause, the conflict-solving inferences follow immediately before any other extension. Deletion is applied eagerly. It does not happen that the strategy neglects inferences on shorter prefixes of the trail to work on longer one. And finally, if we have a fair search plan, all derivations are fair, and we can define the limit of a fair derivation, which of course may be infinite because the problem is only semi-decidable in general. Now, there are three fundamental theorems about SDGs. One says that a descending chain of length-bounded trails is finite. A fair derivation is a descending chain, so we have an ordering on trails to show these two results. Then SDGs is refutationally complete, and it is model complete in the limit. So this is important because if we get a decision procedure from SDGs, it will also provide a model. Now, refutational completeness ensures termination on unsatisfiable inputs. In order to get a decision procedure, we need termination on satisfiable inputs. So there are two ways to achieve this. Either show that the length of the trail during the derivation is bounded, because then we can apply this theorem that says a fair derivation is a descending chain and the descending chain of length-bounded trails is finite. This means basically that in order to go on forever, the method needs to grow the length of the trail. If the length of the trail is bounded, it cannot go on forever. So in this sense, it is well behaved. Sorry. Or else the other way to show termination on satisfiable inputs is to show that only finite remaining extensions can apply. So let's start with the first technique to prove decidability. In order to prove decidability, we need to find a finite subset of the Herbrand base, that is the set of all the ground instances of atoms in the signature, such that all ground instances of all clauses ever appearing on the trail are made of atoms from the bases. Basically, the method has a finite playground if there is a finite basis. It will not generate atoms outside of the basis. Now, we can show that if a fair derivation is in a finite basis, at all stages, the length of the trail is upper bounded by the cardinality of the finite basis. And therefore, by the previous fundamental theorems, a fair SDGs derivation in a finite basis is guaranteed to hold. Now, how to show that we have a decision procedure for a fragment? We need to show that for all sets of clauses in the fragment, we have a finite basis, which in general may depend on the set of clauses. If we manage to do this, any fair strategy will be a model constructing decision procedure for the fragment. Also, we can get the small model property for any fragment that we show decidable in this manner. Why? Because remember that SDGs is model constructing, so if it terminates, the interpretation induced by the final trail is a model. However, this model is a Herbrand interpretation, so it has as domain the Herbrand universe, which in general is infinite. So that alone does not give us a finite model. However, if the derivation is in a finite basis, we can take the set of terms that appear as subterms in the atoms of the basis, and we get a finite set of terms, which gives us a domain, a finite domain for a model. And we don't need anything bigger because we can build this model by determining the truth of atoms from the trail. Now, SDGs decides EPR. Actually, it decides the generalization of EPR to the stratified fragment. This is a fragment that was proposed by Abadi, Rabinovich, and Sagiv in 2010. One assumes a well-founded ordering on sorts, so that if we have a function from a bunch of sorts, these are the sorts of the arguments, S1, Sn, to an image of sort S, then the image of the sort is strictly smaller than all the sorts of the arguments. If we draw a sort dependency graph with an arc from a sort appearing among the arguments to the sort of the image, we get a dependency graph which is a cyclic, which means there are no infinite series of terms such as A, FA, F2 of A, and so on, because we don't have a cycle of length 1, F on itself, and we don't have a cycle of length 2, so we cannot build A, FA, GFA, FGFA, and so on. In this case, the finite basis is the Herbrand base itself, and EPR is just a special case of the stratified fragment with only one sort, because having a well-founded ordering on sorts with this property, if there is only one sort, can be satisfied only by having no function symbols. Now, can we get anything else beyond the stratified fragment? Because we are very happy that we can decide EPR, because EPR is practically relevant, and also the stratified fragment is practically relevant. It was introduced to capture several proof obligations in the alloy system, so stratified fragment is used in verification. But on the other hand, from a technical point of view, it is not too challenging because the Herbrand base is finite. So can we get anything else? So because Sdgs is semantically guided by sign-based interpretation, we consider a property which is useful when the semantic guidance is sign-based, namely ground-preserving clauses. A clause is positively ground-preserving if all the variables that appear in the clause appear in negative literals. Negatively ground-preserving is dual. Why is this property interesting? Because if a set is positively ground-preserving, it means that the positive clauses are ground. Because since all variables must appear in negative literals, the only way for a clause to be positive is to be ground. And positive hyperresolution, since positive hyperresolution only generates positive clauses, will generate only positive ground clauses, And we show that Sdgs does the same. So with I- as guidance, given a positively ground-preserving set, it generates only positive ground clauses. Now let's see an example for restrained clauses, which is the class we are going to show decidable. Suppose that we have this set of clauses with P10, 9, I'm just reading successor n times of 0 as n, and then not PSSXY or PXSY, and finally a negative literal. Now, what we see right away is that in this second clause, the atom PSSXY is larger than the atom PXSY. For example, it is larger in any lexicographic path ordering because SXX is larger than X, but also in any Knuth-Bendix ordering where S has positive weight, because here we have 2 occurrences of S and here only 1. Now, what happens is that Sdgs will generate a ground derivation because the set is ground preserving. It will generate only ground literals. The new literals are ground. And furthermore, they are getting smaller and smaller because, for example, if we put on the trail P10-9 in order to satisfy the first clause, then the following Sdgs extensions will generate the instances of the second clause needed to satisfy it. So, for example, unifying P10-9 with the negative literal of the second clause, we get P8-10, and then we get P6-11, and so on until we find P0-14 and the process terminates, and the last interpretation is a model of these clauses. So we can generalize this concept by introducing a quasi-ordering that we call restraining quasi-ordering that has nice properties. It is stable under substitution. The strict ordering is well-founded. and the equivalence relation has finite equivalence classes. And then we say that a set of clauses is positively restrained if it is positively ground preserving, and for all non-ground positive literals, there is a negative literal that is larger. Why do we consider quasi-ordering and not just a strict ordering? Because by using a quasi-ordering, we can also conquer clauses of this form, differ xy or not differ yx, which embodies a commutativity property, because we can order it by making one literal larger than the other in a recursive path ordering that is compatible with associativity and commutativity. Now we can show that Sdgs decides any restrained fragment, because given such a set of clauses, we can take the set of ground atoms that appear in the set of clauses. We can take as finite basis the set of ground atoms upper bounded in the ordering by those that appear in the input. So we take all the L in the Herbrand base such that there is an M among the ground atoms appearing in the input such that M is greater or equal than L. And then we prove that any fair derivation by Sdgs with a suitable interpretation, that is, if the set is positively ground preserving, it will be I minus, is in this basis. Therefore, it holds, and it is a decision procedure. And furthermore, if the set is satisfiable, it will have a model of this size. So the cardinality of the set of terms, of the set of ground terms extracted from the finite basis plus 1. So for example, the previous set has a cardinality, has a model of cardinality 21. Because if you go back, you see that we have 10 and 19, so we cannot have in a KBO any term with greater than 19 times S, so we get 20 from 0 to 19 plus 1. We can also show by using the finite basis technique that Sdgs decides the positive variable dominated fragment, which is an already known fragment also built on positively ground preserving clauses. The restrained fragment is pretty well behaved because we can show that it is decided also by hyper-resolution. But then the question is, okay, we have this restrained property, but how can we determine that a set of clauses is restrained? The problem can be approached by reducing it to termination of a rewrite system. Now, in general, this is an undecidable problem, of course, but there exist tools such as TT2 or AProve, which allows to determine whether many rewrite systems of interest are terminating or not. So if we have a rewrite system, in fact, a pair of rewrite systems R and E associated to S, such that for all non-ground positive literal, there is a rewrite rule, so that a negative literal is larger in the rewrite relation. So there is a rule rewriting M to L, with the second rewrite system reserved to handle permutative rules, like in the commutativity case for differ. We have a lemma that shows that if this rewrite system is terminating, then S is positively restrained, or else we need a termination of rewriting modulo the rules in E. So we can run experiments. We take problems from the library TPTP version 7.2.0. We take all the problem in the first order formulae category without equality. We reduce them to clausal form, and we get 5,001 benchmarks. Then we wrote a script to generate the rewrite systems from the set of clauses. And we can apply the termination tool to determine whether the rewrite system terminates. Now, on 1,539 inputs, either tool unfortunately timed out, But out of the remaining problems, the determination tool discovered 349 that are restrained, 43 of which do not belong to any other previously known decidable class. Sarah wrote a prototype theorem prover based on SDGs, which is named Koala. It is built on code from Konstantin Korvin's iProver. It uses a discrimination tree for fast unification when performing extension. It implements a failed search plan. It recognizes the stratified problems by checking for acyclicity of the sorts. And it picks I minus or I plus, here there's a typo, there has to be an I plus, based on whether the input is positively or negatively ground preserving, which is used as an approximation of positively or negatively restraining. In the experiments, out of 349 restrained problems that we discovered, Koala determined that 50 are satisfiable and 283 unsatisfiable. We also applied the two PVD problems. There were 351 PVD problems in the fourth category of TPTP. So Koala found 232 unsatisfiable and 76 satisfiable. And furthermore, in that class, there are 1,246 satisfied problems, stratified problems, out of which Koala found 277 satisfiable and 643 unsatisfiable. Now, on the negative side, we found counterexamples showing that SDGs does not decide other fragments such as Ackermann, monadic, FO2, and guarded, which on the other hand can be decided by resolution-based decision procedure based on ordered resolution, but significantly not hyper-resolution, because these sets defeat sign-based semantic guidance. These are the fragments of which Moshe earlier were saying that they didn't find many applications with respect to EPR and stratified, but nonetheless, from the theoretical point of view, they are interesting, so we checked whether SDGs may decide them, but we found counterexamples for each of these. Now, I'm going to wrap it up. So, current work, we are studying a precise relationship between SDGs and hyper-resolution. We already proved that if clauses are ground preserving, SDGs is guaranteed to hold whenever hyper-resolution does. This implies that SDGs decides also the BDI fragment, which is another decidable fragment in first-order logic. Then we discovered new decidable fragments by using SDGs. The sort restrained fragment, which is a generalization of both restrained and stratified fragment, because it is restrained only on cyclic sorts. Sorts that are acyclic are not a problem because of stratification. Similarly, the sort refined PVD fragment, which imposes the PVD condition, positive variable dominated, only on literals in the cyclic sorts. And then the controlled fragment, which is not ground preserving, which is shown decidable, however, only in the Horn case, by using the second approach to decidability that I outlined earlier, namely showing that there are only finitely many SDGs extensions. Then we are also studying modularity of termination and complexity in terms of derivation length. Now, for future work, we are interested in developing the Koala prover with more work on strategies and the basic algorithm inside the prototype. And of course, we are interested in extension to equality, which may come either by embedding superposition in SDGs, hopefully in a conflict-driven way as much as possible, although equality does not lend itself very well to conflict-driven reasoning in general, so there will have to be some compromise. And another exciting possibility is to go in the other direction and embed SDGs in CDSAT, which is our approach for conflict-driven satisfiability in SMT in union of theories. And so we could have SDGs as a module in CDSAT to handle first-order logic or decidable fragments such as EPR. Also, we want to investigate, of course, initial interpretations not based on sign. These are all the references. So the work on decision procedures appeared at DIGCAR in 2020, and we are working on the journal version, whereas SDGs is presented in 2 papers on the Journal of Automated Reasoning. And with this, I would like to thank you very much for your kind attention. Thank you.
So thank you. Let me clap in everyone's name for your nice talk, Maria Paola. It was very fascinating to see new directions in first order logic. So let's open the floor for questions. And I will first read Moshe's question, but you can see, but I think you already answered, because he asked whether you could use your solver for FO2. And you already said that you cannot. Do you want to?
Because I can't. I can't.
Do you want to add maybe explanation why?
Yes, sure. Let me actually go back to the full screen and go back to that slide. So here are the negative results. Mm-hmm. So FO2 is one of the cases where SDGs fails to provide a decision procedure. And basically, we just took a pretty famous example from the paper by Joyner, the paper in JACM 1976. There is a set of clauses which can be obtained by transforming into clausal form a formula which belongs simultaneously to Ackermann, monadic, and FO2. And we can show that SDGs does not terminate on that set of clauses, regardless of whether the interpretation is I plus or I minus. Of course, one could say what SDGs could do if we find a different initial interpretation, and that is actually still open, but at least we can say that it cannot terminate regardless of initial interpretation, because remember that when we say that SDGs is refutationally complete, it is regardless of initial interpretation, and also model completeness in the limit is obtained regardless of initial interpretation. The decidability results, on the other hand, have been obtained for sign-based semantic guidance, that is assuming either I plus, which makes true all the positive literals, or I minus, which makes true all the negative literals. And also the decidability results have been obtained for this sign-based guided interpretation. With those, we know that it does not terminate because we have the counterexample. With some other Browne interpretation, we don't know actually.
Before I ask my questions, I will give a chance others to ask questions, because I think I have a little question that might require more discussion. So is there anyone else who would like to questions? Let's see. Either please raise your hand, unmute yourself, or just start to talk. Let's see. Okay, so maybe then let me start while the others are deciding. Everything was very clear, I guess. So my question is the following. I would like to, you said something that I was not quite, so you said that this is somehow different than standard first order resolutional theorem provers, because resolution as per se does not construct the model. But I somehow always looked as a resolution like really as a model constructing view to the first order logic, because if you think about, you said, okay, it's refutationally complete. I agree, resolution is also refutationally complete. And if you look at the work by Ganzinger and Bachmeier, where they actually introduce ordering on the clauses, and then they, construct model, it is really, actually resolution is refutationally complete, because they are actually describing how to construct the model, and then when you can't construct model, you actually have the proof of unsatisfiability. And the other thing that then I was trying all the time to put parallel between the work that you presented and the exist. And again, going back, right, I have to go back to my background, right, to Gansinger-Bachmeier model construction. So I was then looking, like, when you were describing deletion, that if you don't have too much deletions, that looking back would be probably if you have deleting a clause which is not subsumed by the other clauses, or in their terminology, if you're deleting the clause that is greater than the clause that you already have in the model. So my question is, like, I don't know how familiar you are, or did you already look into parallel between your work and all the results of Gansinger-Bachmeier, where they actually describe how to, where they actually provide foundations of a resolution, and they show easily that it's reputationally complete and how to construct a model. Sorry, it's a bit.
No, it's wonderful.
That is a bit maybe like, let's fight.
Okay, now, if you consider resolution, you see that not only in the work by Bachmeier and Gansinger, but throughout the history of resolution, the refutational completeness of resolution has always been shown by showing that the set of clauses is unsatisfiable because a model construction is bounded to fail. Because if you consider the very first proof of refutational completeness of resolution, the one by Robinson, it was done considering semantic trees. So you have a semantic tree, which is a survey of all possible urban interpretations, and one shows that the resolution collapses it. So that at the end, if the set of clauses is unsatisfiable, it is bounded to get the empty clause, which is like having a semantic tree with only the root labeled by the empty clause. Now, when ordered resolution and ordered paramodulation were introduced, G.H. Young and Mikhail Ruzinovich showed again the refutational completeness of ordered resolution with ordered paramodulation and simplification and subsumption by using transfinite semantic trees, where the transfinite nature of the trees was coming precisely from the addition of equality. Because if you have, for instance, recursive path ordering, you can have infinitely many ground terms before you get to a next bunch of infinitely many ground terms. So the semantic trees had to become transfinite in order to accommodate equality. Then what Bachmeier and Gansinger did with ordered resolution, superposition, ordered paramodulation, and so on, was to propose another model constructing technique, which is the one you mentioned, which is the rewrite model construction. So in the proof of refutational completeness, one shows exactly that if the saturated set by this inference system does not contain the empty clause, then it is satisfiable. And this is done by this model construction argument. So why did I say that resolution is not model constructing, even if in the history of theorem proving, all the proofs of refutational completeness of all the various variants of resolution involve considering a survey of models and showing that if the set of clauses is unsatisfiable, this construction must fail and a contradiction must arise. Because resolution does not build the model explicitly. So the model construction is in the proof of refutational completeness, but when resolution works, it does not build a model. It takes a set of clauses and it generates resolvents and it adds them to the set of clauses, so it expands the set, and then it applies subsumption, simplification, all the contraction rules to reduce the set. But the model is not explicitly represented, okay? Because what you have is a set of clauses, not the representation of a model. On the other hand, in Sdgs, we have a trail of clauses from which at every stage we can read a Herbrand interpretation, which is the initial Herbrand interpretation modified at all the selected literals. So you can actually watch during the run of the prover the model evolving, whereas in resolution it remains implicit. So you cannot work on it explicitly by a mechanism like conflict solving, which solves the conflict between the candidate model and the clause, because you don't see the candidate model. The model construction part is in the proof of refutational completeness, but is not in the operation of the method. Whereas in SDGs, the trail is really the representation of a first-order model. In fact, a partial model, and you get a complete model by completing it. How? By consulting the initial interpretation. That's why we have an initial interpretation. Because otherwise, I mean, the problem in first-order logic is always how to represent finitely a first-order model, right? So we have a partial model, which is on the trail, and then we complete it by looking at the default interpretation. Does this help any?
I don't know. I still somehow, so whenever when I think about resolution, I mean, we do construct models, but maybe it's implementations do not produce models. But looking at some older version, I mean, if you, or even in the Spaß, when you say like as a modern prover, even you will say completion found, and then you will see the set of all saturated clauses. And from this set of saturated clauses, you can actually project back to the model. So maybe, yeah, it's...
Yes, but but a saturated satisfiable set does not give you per se a model. You need to extract it. And it is not always possible, as far as I know. I don't think, I mean, we know that the set is satisfiable, but this does not mean that it represents a model. I mean, this is true of ordered resolution.
Yeah, I think I have to think a little bit about this more. Because we should talk more about that. It's a really fascinating version.
To extract a model from a saturated set, but I don't think they are universal. I believe that the saturated set is satisfiable. That's universally true. If we achieve completion, if we get a finite saturated set without the empty clause, it is satisfiable. That's the theorem.
Yeah.
But it doesn't represent a model per se. Whereas here, the interpretation is spelled out in a sense. It is really the structure, a representation of the model is the structure where the procedure operates. So I don't think it is a difference of implementation. I think it's a difference of operation. Now, of course, you can tell me, but there's still an analogy. And then I'll say yes, because it's the same logic. I mean, it is still first-order logic, so its completeness and the refutational completeness of any method, consider also Tableau, all kinds of methods for first-order logic, there is some similarity in the end because the logic is the same. But if you look at the operation of the method, resolution works by saturation, that is by adding clauses and deleting those that are redundant. Whereas SDGs works by trying to build a model. So it acts lazily only to satisfy one of the clauses that in the input that are not yet satisfied. And it does not generate resolvents, it generates instances. The generation of resolvents is restricted only to conflict solving. So only when there is a conflict between the candidate model and the input clauses, we perform a resolution. Not in general, we don't saturate by doing all the possible resolutions, modulo redundancy, as in ordered resolution and superposition.
It's such a shame that this is not in person, because now we could just go for a coffee break and continue. But this is actually, let's ask one more. Is there maybe someone from the audience says, I gave you a chance, guys, before, but since you didn't ask, I kind of took all Maria Paola's time. So is there any remaining question? If not, then indeed we could go for a coffee, because I think now it's the coffee time at Simon's, but as everything, it's a virtual coffee. So thank you for staying, and we'll see us again next week. Okay.
Thank you very much. Thank you.
Bye, everyone.